Okay, so let's try solving the logistic equation. So the logistic equation, as we talked about it before, was P prime equals Kp m minus P, with the interpretation being that the rate of change of the population is proportional to the current population and also proportional to this m minus P term, which represents the amount of remaining space. That constant m there is the carrying capacity, which you can think of as the max population, and that's why I used the letter m to denote it there. So let's get into this here. So if we do the standard separation of variables idea, then we're going to think of the left as dp dt, and then we're going to separate. So I need to bring this t term over to the right, and I need to bring this other stuff over to the left. So I'll have dp over p m minus p is equal to k times dt, and then I can go ahead and integrate each side of this. And so on the right hand side, we have the easy one. This is just going to be kt plus a constant. On the left hand side, however, we're going to have to figure out how to sort out this dp over pm minus p business. And if it's been a while since you've done integrals, then you may have forgotten, but the technique to do here is partial fractions. So we do a partial fraction decomposition, and we get integral 1 over mp plus m minus p, and then this whole thing is integrated with respect to dp. Now, if you are wondering where I came up with this partial fraction decomposition, well, I did that on a piece of scratch paper. I want you to try it first, see if you can solve it. I'll do it at the end if you get stuck. Anyways, but carrying on from here, I can pull out the common factor of 1 over m, and then we have the integral of 1 over pdp, and we have the integral of 1 over m minus p. And then both of those are just going to be logarithms. So we have 1 over m natural log of p minus natural log of m minus p. And if you're wondering about this minus sign right here, this is because of when we do the u equals m minus p for our change of variables, du is minus dp. So that spits out this minus sign that we have right here. Okay, so then using logarithm arithmetic, this is 1 over m natural log of p over m minus p. Okay, and so that's the guy that is equal to, let's stick another copy of him over here, that's equal to kt plus c. So now I just need to solve for p, see if I can get that guy by itself. And so what will I do? I'll take this m over to the other side. So I have natural log p over m minus p equals mkt plus constant. Now these two c's are actually different. So because this one down below here, it's actually m times the c up above. But since it's an arbitrary constant, I'm doing the usual abusive notation and forgetting about it. So now in order to get rid of the logarithm, I will exponentiate both sides of this equation. And e to a sum, that's the same thing as e to the mkt times e to the c, which is now my new c, e to the mkt. So again, abusive notation. Meanwhile, back on the left-hand side, these guys have canceled out because the exponential and the logarithm functions are inverses. And so we have absolute value p over m minus p is equal to ce to the mkt. And then that means that p over m minus p is plus or minus c, which is now going to be my new c. So this is just updating my constant. And now I need to solve this expression for p. And I end up with p is equal to, isolating for p, m over 1 plus ce to the minus mkt. And that is my solution. So I will do the calculation for the partial fraction decomposition and solving for p in a separate video, but first try to do those on your own.